Hello everyone, in this particular video, let's check the code for CNN, and for doing that, we'll be using MNIST dataset. MNIST dataset is a dataset which is used for handwritten digit recognition. Basically, in this, we'll be having our 10 digits, that is 0, 1, 2, 3, so on till 9. So total, there will be 10 unique digits. Okay, for all of these digits we'll be having the handwritten images. Like for 0, we can write 0 in multiple ways, right? This can be 0, some might write like this, like that. All possible handwritten zeros will be there in our data set, and similarly all possible handwritten ones will be there, and all possible handwritten twos, all possible handwritten threes, and all possible handwritten nines. All these input images will be there along with their corresponding label, that is 0, 1, 2, like that. Okay, and input image will be of shape 28 cross 28. So this is about the dataset that we are having. Now let's try to check the code, and let's see how we are loading the data, and then how we are pre-processing it, and finally building a CNN model for it. Okay, in order to load the data from tensorflow.keras.datasets, we are importing MNIST, and MNIST.load data will be loading our data into xtrain and corresponding labels into ytrain, and similarly testing data into xtest and corresponding labels into ytest. Okay, training data will be loaded into these two, and testing data will be loaded into these two. And then we are just importing matplotlib plot pyplot as plt. And if we wanted to check the shape, as I said, our input shape will be 28 cross 28. And how many such input images are present in the dataset? We are having 60,000 images in the dataset. And similarly, how many testing data points were there in the dataset? There are 10,000 testing data points were there. So, and each is of shape 28 cross 28. And if you want to take any particular image, you can just index it like this. So I'm taking the first training data point, that is xtrain of 0, and in this single image we'll be having the first image from the training data set, and the first image will look something like this. All these will be my pixel values. Okay, and if you observe, the values are varying in the range of 0 to 255. Okay, so in this whole array, or in this whole pixel array, will be having minimum value of 0 and maximum value of 255. Okay, and if you wanted to check that, you can just use max and min functions. So by checking this, here it is giving the maximum value of 255 and minimum value of 0. And the shape we already know, that is 28 cross 28. And if you wanted to check what is present in the image, you can simply use plt.imshow. It is a matplotlib function, and by seeing this, we can clearly understand that it is handwritten digit, that is 5. Okay, and if you check the ytrain, in ytrain the first one is 5, because the image that we are having is handwritten digit 5. So like that, for each and every training data image, we'll be having the corresponding label in the ytrain. And if you check the ytrain shape, it is 60,000, because there are 60,000 training data points. So that's why we will be having 60,000 labels as well. Okay, and similarly, in testing data, we'll be having 10,000 points. That's why we'll be having 10,000 labels in testing data as well. Okay, if you clearly observe, our output is looking like this. That is like numbers like 5, 0, 4, like that. So the values will be between 0 to 9. Okay, and similarly in ytest also, the values will be in between 0 to 9. Okay, but if you check my previous CNN videos, in previous CNN videos, I have already discussed that with the help of CNN, we can solve 3 kinds of problems. That is regression problems, and also we can solve binary classification problems, and also we can solve multi-class classification problems. Now, my question is, what kind of problem it is that we are having? So this MNIST problem is, will it come under regression, binary classification, or multi-class classification? Please comment your answer in the comment section before checking the answer. Basically, it is a multi-class classification problem. Why is that? Because we are having 10 separate classes clearly over here. First class is 0, and then followed by 1, and then 2, and then 3, like that, 4, 5, 6, 7, 8, 9. So all these will be my 10 classes. That's why it is a multi-class classification problem. And according to problem, the place where we'll be making the changes mainly is in the output layer. Okay. And what are the changes that we'll be making in the output layer? First one is the activation function that will be changing. And the other thing that will be changing is number of neurons in the output layer. So these two will be changing in the output layer. And if it is a multi-class classification problem, then the activation function that we'll be using is softmax, whereas the number of neurons that we'll be using is 10. Okay, as this specific problem is having 10 classes, we'll be using 10 neurons for this specific problem. Okay, so I hope this is clear for everyone. This will be clear only if you check my CNN videos. If you haven't seen my videos, then it might not be clear. Please check my concept videos and then look into this particular video. Okay, now as I said, in the output layer, the activation function will be softmax and the number of neurons will be 10. Now let's just see the output layer. The output layer might look something like this. This neuron might be for class 0, and this neuron might be for class 1, and this neuron might be for class 2. Like that, for each class, we'll be having one specific neuron till class 9. Okay, and what is this layer? This is our output layer. And on this output layer, what is the activation function that we'll be using? The activation function that we'll be using is softmax. And what softmax will be doing? I hope this is already known to you by now. Softmax will be giving us probability scores. Okay, so this particular neuron, like after passing it through softmax, here it will be giving us probability score that the given, like let's say previously we are having whole CNN network, and for this CNN network we'll be passing some specific input, right? This specific input is an image, and this image is containing 0. So what is the probability that this image is containing 0, that it will be giving out of this? Okay, and similarly through this neuron we'll be getting probability score of 1. So which means that what is the probability that this image is of 1, that it will be giving. And similarly here it will be giving what is the probability that this image is 2, and similarly here it will be giving what is the probability that this image is 9. Like that, this softmax will be giving how probable is the input is of class 0, and similarly how probable is the input is of class 1. Like that, for each class it will be giving the corresponding probability score. Okay, this is a structure what it will be happening in this particular MNIST case. Okay, and you guys already know all these values will be ranging in between 0 and 1 because it is a probability value, and if we sum up all of these values, it is summing up to 1. Okay, so this is what happens if we apply softmax on the output layer. But here, what is our predicted value? The predicted value of the model is array of 10 values, right? So all these values will be considered as my predicted values. Like let's say my model is predicting it to be 0.8, this 2, because my input image is having, let's say, handwritten digit 2. That's why it is giving 0.8 as this particular probability score, and remaining all are summing up to 0.2. So like that, total the value is summing up to 1, but as the predicted value is 2, it is giving the maximum probability over here. Like that, my predicted value will be present. Now I need to compare this predicted value with the actual value that is present in my data set. Okay, this model will be giving my predicted output, whereas my actual output will be present in the data set itself, right? And what is data set containing? Data set is containing such numbers like 5, 0, 4, all these numbers. But here if you are checking, it is giving probability scores which are in between 0 to 1. And also, how many values are we having? We are having, in the predicted output, we are having an array of size 10, whereas in the actual output we are having single integer value. Okay, it can be something like 2 or whatever label it is. Okay, we need to compare these two. Comparing these two is not possible because it is a single value, whereas this is a 1D array of size 10. So that's why we can't compare these two. In order to make the comparison between these two, what we can do, we can make this into some single dimensional array. Okay, this will be containing the probability scores, and this will be containing exactly what is the number it is representing, like 0, 0, 1, like that. If you wanted to represent 2 in the second index, you can keep 1, and remaining all places you can keep 0. And similarly, if you wanted to represent 3, then in the third index you can keep 1, and in remaining places you can keep all zeros. Like that, you can represent the corresponding output with a 10 sized array. Okay, whereas the predicted output will be containing the probability scores. And if the model is doing very good, then the probability score should be ideally 1 over here, and in remaining cases it should be 0. So that's why we should be giving ideal output, ideal actual output. So ideal actual output, if the class is 2, is should be like this, but the model might be predicting something like 0.8 over here, and in remaining places it might be giving 0. So I hope the point that I'm trying to make over here is clear. So that's why, as we can't compare this predicted value and the actual value, what we are doing, we are making the actual value that is present in dataset into 10 dimensional array. So in order to make that, what we'll be using this particular 2 categorical, can be used in case of doing one hot encoding as well. So to this 2 categorical, we will be passing our y train. On passing our y train, what it will be doing, it will be converting each of these values. Like previously, y train is having a value 5, 0, 4, like that, but now that 5 got converted into 10 sized array, and in this 10 sized array, in the fifth index we'll be having 1, and remaining indexes it will be having 0. Okay, and similarly we can do the same for y test. Y test also we can convert it using 2 categorical to some 10 sized arrays. Like that, we can make our output shape to 10 sized array. Now my shape of output data for training data is 60,000 comma 10, and similarly for testing data is 10,000 comma 10. I hope this is clear till this point. And then we can do data normalization. So basically, if you see, my input data is just an image of shape 28 cross 28, and if you see the values will be the pixel values, which will be ranging in between 0 to 255. But you can do some normalization, and you can make this range of these values to 0 to 1. And in order to do some normalization, what is the formula that we can use? The formula that we can use is x minus min by max minus min. So this is the formula that we can use, right? So here minimum value is 0 and maximum value is 255. So that's why if you keep these min and max, it is giving up to be x by 255, right? So simply we can do this by 255 instead of applying data normalization using some other functions. So that is what we are doing over here. We are just dividing the x train and x test with 255, as the maximum values will be 255. Now, after dividing, the data is getting normalized, and the maximum value will be 1 and minimum value will be 0. And if you check, the input is looking the same. That is because it will not change the overall values. It will maintain the same. This we have already seen in data normalization. If you have seen the data normalization video, I think this point is very clear. The data will look as it is, only the scale gets changed. Now our input shape is 28 cross 28. It is the same. We are just reshaping it because our CNN accepts input to be of 3-dimensional, that is 28 cross 28 cross 1. So the third dimension will be used when it is colored images. Okay, so in case of colored images, we'll be having 3 channels, right? That is RGB. Like that, in case of colored images, this will be 3, or after applying the first convolution, we'll be having 3 dimensions, right? In order to consistently maintain those 3 dimensions, at the start also we need to provide with this extra dimension. Okay, that's why we are reshaping the 28 cross 28 images to 28 cross 28 cross 1. We can reshape both training and testing data. Now finally we are building a CNN model. In CNN, first we can apply convolutional layer, and followed by we can have ReLU layer. Here we are combining both convolutional and ReLU. After that, we are having some pooling layer. After applying one convolution, ReLU, and pooling, we are directly applying flatten. But instead of doing this, we can have extra convolution layer as well. Okay. After applying flatten, then we are making dense layers. So let's see overall shape of this particular CNN. Then you'll get clear idea what are we trying to do over here. Let's say initially we are having input image of shape 28 cross 28 cross 1, and on that what we are doing, we are applying convolution plus ReLU. In case of convolution, what we'll be having something called as kernels, right? How many kernels or how many filters we are having? We are having 32 such filters. And what is the shape of each filter? The shape of each filter is 4 cross 4. This is 4 cross 4, and we're having 32 such 4 cross 4 filters. And what will be the output shape of convolutional layer? For this, we have already seen the formulas, right? So let's say this is n cross n, and this is k cross k. And let's say the number of kernels is m. In that case, my output shape will be n minus k plus 1 cross n minus k plus 1 cross m, right? So I hope this is already known to you. If you didn't know this, that means you haven't watched my previous videos. Please watch them out and then come to this particular video. According to this formula, my output shape will be 28 minus 4 plus 1 cross 28 minus 4 plus 1 cross 32. 32 because for each kernel or for each filter, we'll be having one specific output. That's why my output shape will contain this 32. Okay. So like this, we'll be getting 32 feature maps, each corresponding to one specific filter or kernel. So if you see this, it will be 28 minus 3, which is 25 cross 25 cross 32. So this will be the output shape that I'm getting out of the convolutional layer. And after applying convolution, we can apply ReLU as well. Even after applying ReLU, it remains the same. That is 25 cross 25 cross 32. Now for the next layer or the pooling layer, we'll be having input shape of 25 cross 25 cross 32. And on pooling, what is the shape that we are having? The shape that we are having is 2 cross 2. Or in case of pooling, what is the thing that we'll be having? We'll be having something called as window size. And here the window size is 2. So the 2 cross 2 means that the window size is 2. And if the window size is 2, then what will be my output shape? This you can just think of it as input shape is n cross something, and my kernel size, you can think of this as the kernel size to be k cross k, where the k is 2. Basically, we are just applying the pooling operation, max pooling operation, and just think that this is my k and this is my n, and the stride also to be k, because whatever the window size is, the same will be the stride in case of pooling layers. So that's why the stride will also be k. So in that case, my formula will be n minus k by k plus 1 cross n minus k by k plus 1. If the stride is s, then it will be n minus k by s plus 1. As the stride is k, it will be n minus k by k plus 1. Okay. So these formulas are already explained in my previous videos. Please check them out. So according to this, then what will be my output shape? My output shape will be 25 minus 2 by 2 plus 1 cross 25 minus 2 by 2 plus 1. Okay. And the third dimension will remain the same in case of pooling layers. So only in case of convolutional layers, the third dimension will change. If you evaluate this, 25 minus 2 will be 23, 23 by 2 will be 11, 11 plus 1 will be 12. So that's why my output shape will be 12 cross 32. So this will be the output shape that we get out of pooling. On this particular output shape, what are we doing? We are applying flatten. Okay. So here if you observe, first we are taking the convolutional layer and then pooling layer with pool size of 2,2, and then we are directly applying flatten. So on applying flatten, we'll be having how many number of inputs? We'll be having 12 cross 32 number of inputs, and these inputs are the inputs to the ANN. So from now, the structure that we'll be having is similar to ANN, In ANN, what we'll be adding, we'll be having hidden layers, right? So in the code, we have seen already, we'll be adding the dense layers. So here also we'll be adding the dense layers. Here, what we call the hidden layer as, we call it as fully connected layer. And the first fully connected layer is having how many number of neurons? It is having 128 number of neurons. 1, 2, 3, so on till 128. So this is the first fully connected layer. And then we are having only one extra layer. So that means that this is the output layer. And for this problem in the output layer, we already discussed that there should be 10 neurons. So that's why here there are only 10. And what is the activation function that we'll be using? The activation function that we'll be using is softmax. So on this output layer, the activation function that we'll be using is softmax. And if it is a multi-class classification problem, then what is the loss function that we'll be using? So here out of this, we'll be getting the predicted output, and the loss function that we'll be using is categorical cross entropy. This I have discussed it by this time multiple number of times. That's why I'm not going into much details. So just understand that here the loss function that we'll be using is categorical cross entropy, and optimizer will be using one of the advanced optimizers like Adam, Adagrad, RMS prop, any one of these. Okay, this is my overall shape. Initially, I'm having the input image, and on that input image, I'm applying convolution plus ReLU. So once the convolution plus ReLU is done, then I'm applying max pooling with a window size of 2, and then the output that I got of pooling is this much, that is 12 cross 12 cross 32. On that I'm applying flatten. On applying flatten, here I am having these many number of inputs to the ANN, and then I am having one dense layer followed by the output layer. Now all these will get connected completely like this. These will be the connections that are connecting this particular, this you can think as input layer to the ANN and the fully connected layer over here. And similarly, these will be connected like this. Okay. Now everything is done for this particular CNN. Now, can you guys tell me what will be the number of parameters? So we know that in case of CNN, we are having parameters in this last ANN portion, and then before this, the parameters are only in the convolutional layer, right? So let's see what are the parameters that we are having. We'll calculate the number of parameters that we are having now. So let's say this is the first weight matrix that we are having, that is W1. So in this particular W1, what will be the number of weights? So here if you observe, in this fully connected layer, we are having 128 number of neurons. And in this output layer, we are having 10 neurons. So it will be 128 cross 10 plus we'll be having extra bias terms. The extra bias terms will be 10. Okay, like this we'll be getting total number of weights in this particular fully connected layer and the output layer. Okay, it will be 28 cross 10 plus 10. And let's see what is the number of weights in case of this particular input layer and the fully connected layer. How we can calculate it? The input layer, we are having these many number of inputs, that is 12 cross 12 cross 32 number of inputs cross how many number of neurons are there in this particular fully connected layer. There are 128 number of neurons, so cross 128 plus how many bias terms will be there, as there are these many number of neurons in the fully connected layer, we'll be having the same number of bias terms. So this will be the total number of weights in W2. So after this, after W1 and W2, where we'll be having the weights? In pooling layer, do we have the weights? So in pooling layer, we will not be having any weights. In convolutional layer only, we'll be having the weights. And what are the weights in convolutional layer? Basically, the kernel matrix values. So here, if you observe, there are 32 kernels, and each is of shape 4 cross 4. So the total number of weights will be 32 cross 4 cross 4. Plus, there will be bias terms as well. For each kernel, there is one extra bias term. As there are 32 number of kernels, we'll be having 32 extra bias terms. So this will be the total number of weights in this particular layer. So if you number them, this is, let's say, W1, this is let's say W2, and this is W3. And as I said, in optimizer, what we'll be doing, we'll be adjusting all the weights, right? For adjusting the weights in deep learning, we'll be following some specific way, and that is called as backpropagation. The way we adjust the weights is called as backpropagation. And in case of CNN, first we'll be updating all these W1 according to backpropagation. And after updating all the weights in W1, then we'll be updating all the weights in W2. And after updating all the weights in W2, then we'll be updating all the weights in W3. Okay. All the things that I'm discussing right now can be understood only if you have seen my previous videos. Okay. So this you need to keep it in mind. If you are directly coming it into my code video and if you're seeing it, then some of the points you might not understand clearly. Okay. Check out my theory videos or concept videos. Then you can get it better. Now, once this is done, you can check whether you have calculated the number of parameters correctly or not. That you can do by using model.summary. It will be giving the total number of parameters in each layer. We know that in convolutional layer, there are some parameters. And if you sum up, if you calculate that 4 cross 4 cross 32 plus 32, it will be summing up to 544. And similarly, if you sum up all of these in W2, that is 12 cross 32 cross 128 plus 128, then it will be summing up to this much. And similarly, if you calculate total weights in W1, that is 28 into 10, it will be 1280 plus 10, it will be 1290. So that is the exact number that is present over here. Like that, you're calculating the number of parameters. You can check whether you have calculated correctly or not using model summary. I always recommend you to know how to calculate the number of parameters. That means that you have understood the model clearly. Okay. If you understood about the model clearly, you will be definitely able to calculate the number of parameters correctly. So that's why I always recommend you to know how to calculate the number of parameters for each and every algorithm that you are trying to learn. Okay, or each and every machine learning algorithm or deep learning algorithm that you are trying to learn. That you can calculate the number of parameters. And after that, as you already know, the loss that we'll be using is categorical cross entropy. And the optimizer that we'll be using over here is Atom. And metrics, you can use something like accuracy, or you can go for precision, recall, F1 score, all those as well. And here we are using early stopping, and we are asking it to monitor validation loss, and the patience we are making it to be 2. And then we are fitting it, and we are mentioning the epochs to be 10. But it is not even running for 10 epochs. That is because we are using early stopping. So it is stopping after 7 epochs. And let's see what is the amount of accuracy that we are getting. By 7 epochs itself, the accuracy that we are getting is near to 99% on the training data. And on testing data, we are getting it to be 96%. So that means our model is performing really well. Okay. So this is our loss graph. This blue one is telling about the training loss, whereas this orange one is telling about the validation loss. So as the validation loss is slowly increasing, we are stopping the model here itself according to L stopping. And similarly, accuracy also, my validation loss is increasing and then slowly reducing. So that's why we are stopping at this 6th epoch itself or 7th epoch itself. Okay. And you can evaluate the same on testing data as well. You can pass your actual testing data, and also you can pass your actual outputs of the testing data. Then you'll be getting the corresponding accuracy. Or if you wanted to predict the values for testing data or any other data, you can simply pass your X test or the corresponding input data. Then it will be giving us the prediction values. So basically, as the prediction is of softmax, it will be having a 10 sized array, and the values will be in the range of 0, in between 0 and 1. So in order to get the exact predicted value, you need to use argmax. What argmax will be doing? Argmax will be giving us the index for which there is maximum value. So basically, in all of these, whichever is the maximum, that is our predicted value, right? So in order to get that particular value, you can simply use this argmax. So then it will be telling us the class that it is predicting is to be 7. Like that, you will understand what class the model is predicting, right? And you can use classification report. We are passing actual data, that is y-test, and y-test predicted, that is the predicted data. So in predicted classes, we'll be having the exact numbers. That is because we are doing argmax. So on doing argmax, we'll be getting all the predicted classes numbers. So on applying this classification report, you'll get to know what is the accuracy what is the, here you are having the accuracy on the testing data, and these are all the precision, recall, and F1 scores for the corresponding classes. So for each and every separate class, we'll be having precision, recall, and F1 score separately. So this I have told you before itself. I hope you have seen all of my videos. If you have seen, then all of this will be very clear for you. And then if you check the confusion matrix, it will look something like this. And similarly, on training data also, if you wanted to predict, you can simply use model.predict, and you can pass the xtrain, that is the input data. Then it will be giving us the predictions. And the predictions will be in the shape of 10 because the output is of softmax. So that's why you can apply argmax in order to get the exact value of the prediction. And then finally, you can do classification report on the training data also. So most of the time on training data, it is giving 100% accuracy that we can observe from this particular classification report. There are some misclassified points, but most of the time it is giving 1. That's why it is showing it to be 1. And also, if you wanted to pass some inference image, then you can take that particular inference image and check the maximum and minimum value, because before passing it to the model, we are normalizing it. So that's why you need to check before directly giving the inference image. On the inference image, if the maximum value is 255, then you need to normalize it, and then you need to pass it to the model. So as it is 1 and 0, there is no need for us to normalization. So that's why we are just checking the image, and then we are passing it to the modular predict, and it is predicting it to be 7. Okay, so like that you can code for some CNN problem. Here we are using only one convolutional layer, but in other cases it can have more number of convolutional layers as well. So that's it for this particular video. Thank you everyone. Bye bye.